Hi. Part 2 of Hyperbolic. Let's see how many of these we need. So the network exploded and patch it up. Let's go. So these 2's cancel. The left-hand side stays as is because there is nothing you can do. And the right-hand side now has single divided by 2. And the top, we have to FOIL. Good. So e to the x times e to the x is e to the x plus x, which is e to the 2x. E to the x times e to the negative x is going to be plus e to the 0, which is 1. Then e negative is minus 2x. So now both of these are 1, but they cancel because it's positive e to the 0 minus negative e to the 0. And we get left side equal to the right side, and the identity is proved. Right? 2x minus e to the minus 2x divided by 2 is e to the 2x minus e to the minus 2x divided by 2. And we have the solution. Of course, math. Yes?
Can you explain the flowers and hearts? I didn't follow that.
So, this over here is called the argument of the function. You have these things under the square root. You have it following the sine. You have it following ln. So that's called the argument. And the reason why I put a flower rather than x is because you need to understand that whatever is here goes into these. Good one. So whatever is there goes into these. This is why I didn't put an x. Same thing with the heart, right, on this side. So we are using the same formula to expand sine hyperbolic of 2x and sine hyperbolic of x, except the argument is different. So we are using the same form of the equation. What is going to be the flower? Where on the left-hand side the flower was 2x, on the right-hand side for the sine the flower was single x. I can have 3x. I can have a completely different function. I can have x squared there, right? So that's why I put a flower. Now, what else? Let's do another one, because we can. Which one? Number?
4.
4. Yeah, 4. All right. So we have, for number 4, before we start number 4, please, let's all go grab the wrist and do 10 rotations, because we do not want the carpal tunnel on this proof. Right? Then you put the hand this way, palm towards me. You take this one like a handshake and you pull it this way to stretch all of these, right, like that. Perfect. Shake it off and let's go number 4. Start a new notebook. Cosine hyperbolic of x plus y is equal to cosine hyperbolic x cosine hyperbolic y plus sine hyperbolic x sine hyperbolic y. We need to replace all 5 of these with ease and then do a whole bunch of foiling and combine like terms, and hopefully we'll be done at the end. Now here it goes with the hearts and flowers. In this case, the flower is, the heart for the cosine, right, is x plus y. So I have e to the x plus y plus e to the negative x plus y in parentheses divided by 2. That is my left-hand side. And as you can see, the exponent of e now takes x plus y. On the right-hand side, I just have x's and y's. So I will go and say e to the x plus e to the negative x over 2. And then e to the y plus e to the negative y over 2. So that's this one, and that's that one. Then we have this big fat plus over here, which is that plus. And then we have the two signs. Those have minus in between e's. So e to the x minus e to the minus x over 2. Did I mention you should put the notebook sideways, like the landscape? No? Sorry. E, because I can generate paper infinitely. You can't. E to the y minus e to the minus y over 2. There we go. So that is us setting up the problem. Now we have to go FOIL, like terms, and all that kind of stuff. All right, so there is nothing we can do to the left side, so we get to copy that one, e to the x plus y, with or without parentheses, plus e to the minus x plus y, absolutely have to have parentheses there, divided by 2. The right-hand side, do we all see that we have a 4 and a 4 common denominator? Right? We see that? So I'm just going to go wee and say 4. Yeah, 2 is not equal to 4, but give it a chance. All right. Patience, young Padawan. So what do we do? Well, now it's time to FOIL. I have these two to FOIL and these two to FOIL with the plus in between, right? So let's go one by one. FOILing the first one. E to the x times e to the y. What is the rule in algebra? When you're multiplying same bases, exponents add. Good. So e to the x plus y, when I multiply this times that, exponents add because it's the same base. Then I have this times this, and you clearly have plus e to the x minus y, because when you add exponents, you're adding x plus negative y. That's what you get. Now the inner ones, you have plus e to the negative x plus y, and multiply the last ones, which is plus e to the negative x minus y. So guys, that's just doing this piece here. Now we have that big fat plus, and we have another one of these divided by 4 for the second fraction that we need to FOIL. Yeah, landscape on notebook. So now FOIL this. E to the x times e to the y is e to the x plus y. E to the x times negative e, so it's going to be negative e to the x minus y. Inner ones, minus e minus x plus y, and negative times negative is a positive e minus x minus y. If you're experiencing anxiety by now, look at something else for a second. Maybe I should pull up a picture of a puppy. And we're getting there. Left-hand side doesn't change, right? There's nothing done to it. On the right-hand side, your common denominator is 4. Now, look at some of these terms. You see these ones? They cancel, right? these guys cancel. And in blue, these guys cancel. The other ones stack up. So this is 2e to the x plus y plus 2e to the negative x minus y. Okay, well that was now simplified, right? So e to the x plus y plus e to the negative x plus y divided by 2. And now over here I can factor out 2 and have e to the x plus y plus e, and I can factor the minus sign and have x plus y here divided by 4. Now these two cancel, you get a 2, and there they are, equal e to the x plus y plus e to the minus x plus y divided by 2 equals e to the x plus y plus e to the negative x plus y divided by 2. So that's you prove identity when you get the same expression on the left and the right. This problem is awesome for killing time, carpal tunnel, and if anyone knows you during the Thanksgiving dinner, lead with this. And they say, oh, I haven't seen you for a year. How are you? What's new? Say no more. Let's work out this identity. What's new? Hyperbolic functions, and we can start with this identity here. That's the idea. It frees up a lot of time for video games.
You should tell my brother.
Great. So that were 2 proofs out of 12 that are there. Some are obviously much shorter than this. I don't think there is anything longer than this, actually. It's probably the longest one you write. But your book graced you with a whole bunch of problems that you can use is to show that the expression there is an identity, always true, or not true, right? So some problems for homework might say, is this expression true? Meaning, if you are to work out this expression, are you able to put it down to left side equals the right side? And that pretty much takes care of the first part of the lecture, where we introduce hyperbolic functions and we take a look at their graphs and properties, understand they are nothing like trig because they are not periodic, and then still say, but they're similar because they have trig-like identities. List those identities, understand that those identities are annoyingly close to what you have for trig, and then do some identities. Part 2 of the lecture is to work out derivatives and integrals of hyperbolic functions, and also briefly mention in part 3 of the lecture that there are inverse hyperbolic functions that you will never use, but they're there, right? So let's mention.
So do we take a break?
Oh, you want a break?
I don't know.
You guys want a break?
It seemed like we're closing out or something.
Closing out?
Yeah. Or 9.51 we just learned all of this.
More than 300 seconds.
So, do you want a break or you don't want a break? Oh my God, you can't even decide that. How are you going to choose the date now for the exam? Okay, fine. No break, we go home early. Great. Okay, fine. Solve. Calc of hyperbolic. Calc for hyperbolic functions, with hyperbolic functions, of hyperbolic functions. You can swap this word with whatever you think works better. Anyway. The book gives you one chart with all 12 formulas, and I'm tempted to do the same because they behave the same way as trig functions do. They're all paired and they actually have exactly the same deal like trigs, except minus signs are in different spots. Fun. So let's list, one chart with 12 equations so we can actually see going forward, going backward. And then do some examples. Well, calculus. We have derivatives, we have integrals. Limits are not so crazy important because you can always calculate limit by calculating the y value. That's what the limit is, right? Fancy way to calculate the y value. So we don't have to worry about the limit. We worry about derivatives and integrals. Now, the pairing of functions is important. So I will just say calc pairs sine hyperbolic and cosine hyperbolic, secant hyperbolic with tangent hyperbolic, and cosecant hyperbolic with cotangent hyperbolic. Guys, it's the same pairing like for trig. And now we get to see all 12 calculus equations in one box. Number 1 and 2 is going to be the derivative of sine hyperbolic of x is equal to cosine hyperbolic of x. Happy so far. This means that the integral of cosine hyperbolic x dx is equal to sine hyperbolic x plus c. That's the first two equations. Same as trig, right? Erase those ages, same like trig. All right, let's do something different now. The derivative of cosine hyperbolic x is positive sine. I know, hyperbolic x. Now that means that on the integral sign, on the integral side, you also don't get the negative. So sine goes to cosine, cosine hyperbolic, hyperbolic sine, hyperbolic cosine. Either way you do derivatives, integrals, no minus signs anywhere. Line number 3, the derivative of tangent hyperbolic x is secant hyperbolic squared x, exactly the same as your trig. And now the integral of secant hyperbolic squared x dx is going to be give you tangent hyperbolic x plus c. Number 4 is the cotangent. So cotangent hyperbolic x is going to give you negative cosecant hyperbolic squared x, which gives us that the cosecant hyperbolic squared x dx is equal to negative cotangent hyperbolic x plus c. Nice one. Number 5, the derivative of secant hyperbolic x is going to be negative secant hyperbolic x tangent hyperbolic x. You remember this formula from trig, and it didn't have minus. This one does. So that's the difference. the integral of secant hyperbolic x tangent hyperbolic x dx is equal to negative secant hyperbolic x plus c. And the last one is, last formula is the cosecant. So it's a cosecant hyperbolic x, which is negative cosecant hyperbolic x cotangent hyperbolic x, giving us the integral of cosecant hyperbolic x cotangent hyperbolic x dx to be the negative cosecant hyperbolic x plus c. Ta-da! What are the two skills that you need to pull this off? Well, you have the chain rule and you have the U sub. Now, before I remove this from large screen, you are encouraged to take the picture with your cell phone. So you have this on a quick draw. You are welcome to walk. There's a blue line over there, right? So take the photos of this.
Open phone. Open phone.
Just stand underneath and go like this.
Oh, in the glory, like,
Photo bomb.
yeah, photo bomb.
You're just holding all the
Yeah.
It's like when people try to hold
When they go to DC and you put the finger on top of the Washington Monument,
oh yeah.
all cute, right? Like, really?
People are holding up the Leaning Tower of Pisa.
Oh yeah, pushing it back. Yeah, that's
Good one. It's pretty creative. It's pretty fun.
all right. Paparazzi moment done. Good. So now we're going to practice few of these examples using, as I said, chain rule and using the U sub, because those are the two techniques that you will use with these formulas. To help out here, I'm going to write the modified number one. So earlier, number one said the derivative of sine hyperbolic of x. Well, no, of f of x. Because you can have sine hyperbolic of x squared, sine hyperbolic of ln x, sine hyperbolic of, sine hyperbolic of sine x. Just to make, oh, that one made you twitch, right? I know. So you are using basic chain rule here, where the derivative of sine hyperbolic is the cosine hyperbolic of f of x times the derivative of f of x, which was the argument, right? So that's number one modified, and then modifying it for u substitution, right? It's integral of f prime of x cosine hyperbolic of f of x dx will give you just sine hyperbolic on as well, because you have the number one for derivatives and number one for integrals. And now you can modify all 12 equations, right? This is like 1a and 1b, right? Because you have derivative formula. And so let's practice this. Say, right, you finally graduated, you got your job, 9 to 5, it's engineering company, and your boss shows up, right? I need this differentiated. Right? Because that's what your job is, right? You went to school and you learned for 4 years to differentiate examples. So boss wants you to differentiate the secant hyperbolic of x squared plus 3. And then once you're done, you can take your break.
How much am I getting paid for this?
How much? Obviously, less than $300, because that's how much the office computer is that can run Wolfram Alpha on it on the website to do the same thing. Okay, so you are getting paid less than $300 for the lifetime of you working there, if this is your job. Anyway, and you have to do it less than a second because the computer wins.
I was done before you.
We have a secant, and the derivative of secant is negative secant tangent. So, negative secant hyperbolic of x squared plus 3, tangent hyperbolic of x squared plus 3, times the derivative of the inside, which is 2x. So the total answer over here is negative. Attitude doesn't help. 2x. You just have to know this stuff. So, leg again. No, caught up. Nice. We used chain rule, which is what you learn in Calculus 1, to take the derivative and then following the derivative of the inside of the function to deal with this. Let's practice another one of these. So what is the derivative of x squared times cosine hyperbolic of square root of x, just to be pest? What do we have? Yes? Beautiful. We have product rule. There are two functions. There is a function x squared, which is multiplied by cosine hyperbolic. So this problem is a product rule, which you learn in chapter 3 in Calc 1. So let's go. Copy the first one, which is x squared, times the derivative of the second, which is derivative of cosine hyperbolic, is sine hyperbolic, root x, and then you have to take the derivative of this one as a chain rule, which is 1 over 2 root x. Right, so chain rule gives you that one. Plus, copy the second one, which is cosine hyperbolic root x, times the derivative of the first, which is 2x. Those of you who forgot the product rule, this is your u, this is your v. You have your u, v prime, plus v, u prime, if you forgot the product rule. U and v are the entire function, and then there are individual derivatives for each one of them whenever they need it. So now we simplify this mess as much as we can. I have, as you can see, x squared divided by square root. So that's 2 minus a half, which is 3 halves. So x to the 3 halves divided by 2 sine hyperbolic root x plus 2x cosine hyperbolic root x. Done. Yes?
Like, if we just leave it as the unsimplified, is that fine?
Yeah, it breaks my heart. See, Personally, I should say I don't care, right? But then some people are computer science majors. And for them, it's extremely important to simplify it. Why? Because what does it mean to optimize a software? Yeah. If the computer has to do less calculations, it performs faster. So you make your computer faster by optimizing the software or building the faster hardware. Hardware is hitting a ceiling, pretty much. What you can buy today? You can buy a 16-core processor to run in your home machine, right? For $500. 60, yeah. So if you calculate the amount of operations that need to be done, if you are a computer science major, your job is to always algebraically simplify your mathematical equations. The less the computer has to do, the faster it works, right? Because computers do millions of these calculations, and if they do the million calculations 10,000 times, you're reducing something. You reduce 10,000 operations, let's say, right? By simplifying one formula if you run it 10,000 times, right? So you do want to make sure that there are less calculations every time you do something. Now, for the rest of you, right? Now, are you a computer science major? No? It's like, I'm not saying that. It's going to be the mystery. Right? Didn't I say we're not all equal? Right? So that's the point where I can say, oh, you're a computer science major, you didn't simplify, -2. Electrical engineering major, don't worry about it. Hey, that's not fair. I know, you picked the major. I mean, what? I'm going to be now waiting for computer to slowly process something because you're not simplifying mathematical equations in your software? Yeah, -2, my friend. Or you can change to electrical or mechanical. I don't care then, right? All right. How about some integrals? We can do that. That's fun, right? How about the integral of that? We don't have to start with like a diabolical problem right away. Let's do sine hyperbolic raised to the 9th power of x cosine hyperbolic x dx. There we go. We start simple. Yes. Would you like a different number? I can put 19, 190.
9 is 9.
It's all the same. I mean, you're just gonna do +1. So what do we have? What do we do?
Let me change one, right?
Backwards, which is called what? For integral.
I forget what it's called.
U-sub. It's called U-sub.
U-sub.
Yeah. Yeah, backwards chain rule, right? So U substitution, right? If you make sine hyperbolic to be U, you have cosine for du, and everyone is happy. So U equals sine hyperbolic x, du equals cosine hyperbolic x dx. So if you take a look at the peanut over here and the peanut over here, same peanut. So if you're allergic to the stuff, then we'll let the natural selection deal with that. U to the 9 du, which is u to the 10 over 10 plus c. Now we have to go to the original variable, so I don't care about u, care about the x, right? So we go and say sine hyperbolic to the 10 x plus c. Let's say you care, right? How would you check? Take the derivative of the orange box. If you land with this, perfect. Just like every other integral. There is no excuse not to have 100 on the first test. There's no excuse because you have two integration techniques. basic and u sub. And every question is the integral, and every answer you get, you can differentiate and see if you're getting this thing. So I don't really see how you can even fit the 99 as a as the grade on the exam, because you can check everything and just arrogantly walk out and say this is 100, because I can't really come up with the argument I really don't like you, so like -10, right? Because my opinion doesn't matter, right? You just solved all 10 problems 100% correct, so it's 100. Let's see what else. How about how about x times secant hyperbolic squared x squared dx? See if you can untangle this one. I just thought of it while standing over there. You saw me, right? And the answer is
1/2 tan h x squared plus c.
very good. Yeah, obviously. 1/2 tangent hyperbolic x squared plus c. Good.
You do it.
Of course I can. Like this. He did too. So when you look at the integral, the trick is always to look for function derivative pair. Function part of that pair will be your u sub. What I see here is the single hyperbolic function, not linked to anything else. Definitely cannot be a part of my u sub. And then I run into two functions that are comparable to be a function and its derivative. So if I'm looking for function derivative pair, I have x squared and x. It should be 2x, but we can fudge that. So when I look at the problem, look at the previous problem. I have 1, 2 hyperbolic functions. They are derivatives of each other. Therefore, function derivative pair, I have 2 hyperbolic functions. The next example, one we are looking at right now, I only have a single hyperbolic function, which means it cannot participate in function derivative pair. Hopefully I have something else, and there it is, x squared and x. So u is always the function, which is in this case x squared. du is 2x dx. I don't have 2x, so I have to fix that, and that is where that 1/2 spawned. So now I have 1/2 integral, and this 2x dx, right? If I put that into this peanut, 2x dx is du, and the secant squared of u, right? Because x squared is u. So I have secant hyperbolic squared u du. And that is a basic hyperbolic integral of 1/2 tangent hyperbolic u plus c. We replace u with x, so 1/2 tangent hyperbolic x squared plus c. Done deal. Let's take a look at an example that they might have in the homework somewhere. Oh, may I suggest disk method, shell method, area between two curves, area surface revolution. With these functions, all of it works, right? Oh, beautiful. Look at this. Lock the doors. Integral 0 to ln2 of tangent hyperbolic x dx. Integral, definite integral, of tangent. Let's go look at the integrals on that list I gave you. Is there an integral of a tangent on the list of integrals? No. Good. Is integral of a tangent hyperbolic a basic function? No. Okay, so how do I do this problem? Beautiful. Sine hyperbolic over cosine hyperbolic, and then what? Use substitution, I heard it. What's u? Good. U is cosine hyperbolic. What's du? Excellent. Sine hyperbolic x dx. Beautiful. Now, if I'm going to swap these, I might as well swap the limits now, so I don't have to go back to x to compute this. I can just do the integral in terms of u, and if I have my limits in terms of u, I can just compute, right? Right. So, u1 is going to be cosine hyperbolic of 0. How much is that? How much is cosine hyperbolic of 0? One. Why 1?
Because you're fancy graphs.
because of my fancy graphs. I love that. He remembered that the graph from cosine hyperbolic, when x was 0, he remembers that it cut through 1. Do we need to memorize that? No. We know the formula of what cosine hyperbolic is through ease. And you replace x equals 0 in ease. So sure, this is equal to 1, but let's just go and say e to the 0. Right? I'm going to go e to the 0 plus e to the negative 0, which is still 0, divided by 2. That's 1 plus 1 over 2, and the whole thing is 1. So now, when I start writing my problem over here, I have integral from 1, and I have du over u inside, and now I have to calculate the upper limit, which is u2, which is cosine hyperbolic of ln 2. How much is that? Now, fancy graph is not going to help here. So, e to the ln 2 plus e to the minus ln 2 divided by 2. Remember how I said cosine hyperbolic of a heart is e to the heart? Right? So if I have x, heart is x. If I have ln 2, it's e to the ln 2. Whatever is the argument of cosine hyperbolic becomes the exponent of e, which is why we did those exercises over there. Okay, that's cool. E and ln cancel, leaves 2 behind. Plus, the negative makes the 2 into a half, so this is a half divided by 2, which is 1 plus quarter, for a total of 5 quarters, and that's your upper limit, 5 quarters. What's the integral of du over u? Nice. ln absolute value u, 1 to 5 quarters. This is going to be ln of 1 minus, no, lies, ln of 5 quarters minus ln of 1. And how much is ln of 1? 0. Beautiful. Because ln of 1, right? It cuts through 1. So y value is 0. And the answer is ln of 5 quarters. No plus c. It's a definite integral, right? So you're getting a number. You can punch this in the calculator, right? ln 5 divided by 4. And you get decimals if you are anxious. Cool? Of course. And now I want to go and find particular problem in the book, and then we're done. So give me an hour, I'll be right with you. There it is. All right. Ready? So we are closing the evening with a little bit of a review for the upcoming exam. You still haven't told me the date, but it's upcoming, right? Find the length of the curve for y equals 1/2 e to the x plus e to the minus x on negative ln2 to ln2. This problem is in section 6.5, length of curves. It's like a little review, right, to get us into exam mood.
So it's like y is equal to cosine of
Yep.
and then you just figure out.
So if you were to do this as a homework problem in 6.5, you have to shovel these e's and separate functions and worry about the half and all of this. What have you learned tonight? You learned that this function over here is also written as a cosine hyperbolic x. And now you get to play with that one. Right? So, what do we have? Nice one. Y is cosine hyperbolic x, because we just learned that. We need the y prime, which is sine hyperbolic x, because that is what goes into our equation. And then we are going to now set up the integral for length of the curve from negative ln2 to positive ln2 of the square root of 1 plus sine hyperbolic squared x dx. Nice. Now, some of you might remember the identity which said that cosine hyperbolic squared x plus sine hyperbolic squared x is equal to 1. No, that's a lie. It's a minus. Sorry. It's a minus on the formula. So, what do we know from there now?
That everything is sine.
We know that when you move sine to this sign, cosine squared hyperbolic x is 1 plus sine hyperbolic squared x. So this integral turns into a joke. Right? You have your ln2 square root of cosine hyperbolic squared x dx, which is where square kills the root. And you just have the integral of cosine hyperbolic, which is sine hyperbolic x computed from negative ln2 to positive ln2. This becomes sine hyperbolic of ln2. Oops. Minus and minus will give you a plus. Another sine hyperbolic of ln2. Sine hyperbolic is odd function, which means that the negative of ln escapes in front and adds to the subtraction from the integral solution, right? And we get 2 sine hyperbolic of ln2. Now we all know that sine hyperbolic is e to the ln2 minus e to the minus ln2 over 2. Now these guys drop. The first one is just 2 because ln and e cancel. The second one will make a half because the negative goes inside the ln, makes the ln of a half, and then ln and e cancel, and you just add a half over there, and the whole thing is 3 halves. What is 3 halves? The cable sag, right? Didn't we talk about the cosine hyperbolic being the polynomial looking function? Anytime you put the cable, pin the cable on 2 ends, it's going to sag according to the cosine hyperbolic. Well, I have the cosine hyperbolic function, and I have 2 values along the x-axis where those are pinned. So this problem just calculated the length of the cord, and this is what electrical engineers use to calculate the length of the cable that you need to stretch between two power towers so you guys and I can all charge our phones eventually at home, right? I mean, and plug whatever else needs to be plugged into the wall. Good. That's it for 7.3. That's it for chapter 6. That's it for chapter 7. We are ready for the first exam. Bye.